Hi and welcome to the 7th video of BIOB20. In this video, we're first going to showcase the central limit theorem. As you know, we can sample from the Gaussian or normal distribution with the function rnorm. We can plot the histogram of a relatively large sample with 10,000 random numbers with the function hist. We obtain the typical Gaussian shape, the bell curve, but we can increase the resolution by changing the parameter breaks so that we can get a smoother version of it. Breaks equals 50 gives us a good look on the normal distribution. Now we're going to investigate what happens to the histogram when we take the average of multiple random numbers. For this, I can use the function replicate and asking for 10,000 random numbers. And I'm going to use the function rnorm with 5 random numbers and take the mean. This will generate 10,000 random means of 5 Gaussian random numbers. If I plot the histogram of this new random sample, I obtain a perfect Gaussian distribution. This is expected. The average of Gaussian random numbers is itself a Gaussian random number. Now let's look at what happens to the histogram if I don't take Gaussian random numbers to start with, but something else. I could say, for instance, that I want to take uniform random numbers. And let's see what happens if I take the average over a small sample, like size equals 3, for instance. We get a histogram which is clearly not uniform, and that kind of want to be Gaussian, but this is not really completely Gaussian. It's a little bit too fat on the sides to be Gaussian. Let's see what happens if we take the mean over a bigger sample, like a size 10 for instance. In this case, the distribution looks almost Gaussian. If I increase the sample size to 20, I get a distribution which is indistinguishable from a Gaussian already. This shows that taking the average of Gaussian random numbers gives you a Gaussian distribution. But we've also seen that if you take the average of uniform random numbers, you also get a Gaussian distribution, provided the sample size is large enough. What about other distributions? What is going to happen, for instance, if I use the exponential distribution instead of the uniform? If we take the average over 3 exponential numbers and do this 10,000 times, we obtain a histogram which is clearly not Gaussian. This is completely asymmetric and it looks more like the gamma distribution. Let's see what happens when we increase the sample size to 10, for instance. The shape of the histogram is less asymmetric, but this is still clearly not Gaussian. If I increase the sample size to 20, we get a distribution that starts to look like a Gaussian. It is still asymmetric, but it could at least be compared to a Gaussian in this case. And if we increase the sample size to 50, we get a good approximation of the Gaussian distribution. There is still a little bit of a tail on the right side, but otherwise the bulk of the distribution is more or less symmetric now. This is the essence of the central limit theorem. It says that it does not really depend which function you take to start with. If you take the average over large enough samples, you will get a Gaussian distribution. What is considered large enough depends on the distribution you start from. In the case of the uniform distribution, we can see that 1020 already gives an okay approximation. In the case of the exponential distribution, you need to go a bit higher, like 50 or so. When the starting distribution is symmetric, the convergence is relatively fast. Samples of size 20 or so already give a good Gaussian approximation. When the starting distribution is asymmetric, we need to have samples of a bigger size before the Gaussian approximation starts to hold. In conclusion, the central limit theorem says that we can often consider that the mean of a random sample has a Gaussian distribution, provided the sample is large enough. We will see in the tutorial that this can be very useful. Next, I would like to introduce the concept of the for loop. This is a standard feature of programming languages, and R is no exception. We have seen that there is an easy way to create a vector of consecutive numbers with the colon notation. This is something that we'll be using all the time when we create a for loop. To create a for loop, we start with the keyword for. Then we designate a variable, which I'm going to call I, and that represents an index that will take all the values inside the vector that we will define. Then we define a vector that will typically use the colon notation. This defines the header of the loop. In this case, I will successively take the values 1, 2, 3, 4, and 5. We then create the body of the loop between curly braces. The body of the loop will be executed multiple times with different values of I, the variable that we've used in the header. I can do something simple, like print I, for instance. When I press enter, you can see that the block is evaluated 5 times. These are 5 vectors of size 1 and not 1 vector of size 5. The command print has been executed 5 times, and the argument I has taken 5 different values from 1 to 5. It is possible to modify I within the body of the loop. For instance, I can say print I squared instead of I. There's no problem with modifying I inside the body. You can see that we get the squared numbers as expected. But the most useful aspects of for loops is that we can use I for indexing other vectors. To construct an example, I will define a variable x which contains 5 random Gaussian numbers. The numbers are shown here. In the for loop, we can use I in order to access the elements of x. For instance, we can say print x at position I. I get the elements of x one at a time. What is even more interesting is that I can use the I variable of the for loop to modify the elements of x at position I. For instance, I can say that x at position I should be equal to I. This time when I press enter, nothing happens because there is no print statement within the body of the loop. But the operations have still been executed. If I look at the vector x, you can see that it now contains the values from 1 to 5. In summary, for loops are really useful to access and modify the elements of a vector. I'm now going to give an example of how we can use for loops to solve statistical problems. To create an example to work with, I load in my session an unknown quantity which is called SZ. I am then creating a new random number using the binomial distribution where the size is equal to this unknown parameter SZ. And we could say that the parameter prob is equal to 0.3, for instance. The result is 13. And now we would like to know what is the most plausible value of SZ. To start solving this problem, I need to be able to compute binomial probabilities. This is given by the function dbinom, and I need to specify x, which is 13 in this case, and the size, which I'm going to set to any value, like 34. And prob has to remain 0.3. Here I see that if SZ is equal to 34, there is an 8.2% chance of obtaining 13. We now need to find the value of size, which makes this probability the highest. We could do this manually, but it works better with a for loop. I am creating a vector LL for log likelihood, and I fill it with 150 zeros with the function rep. This is the initialization of the vector. I then start a for loop with I running from 1 to 150, where I compute the probability for every value of size from 1 to 150. I recycle the command from before, and I replace size equals 34 by size equals I. This way, size will successively take all the values from 1 to 150. And because I want the log likelihood, I specify log equals true. And each value I put in the position I of the vector LL. This runs relatively fast and I can plot the results. The x values are every number from 1 to 150, and the y values are simply LL. I obtain a typical log likelihood curve, and we can see that the maximum log likelihood is reached for approximately 48. So this is the most plausible value of SZ given the information that I have. I can say that SZ equals 48 is the maximum likelihood estimate. In this example, we can see how the for loop helps automate the computation of the log likelihood so that we can plot it in a nice way. Another important aspect of computer programming is the if statement. The keyword of an if statement is if, followed by some condition. And this condition has to evaluate to either true or false. Then between curly braces comes the body of the if statement, which is executed only if the condition is true. If the condition is true, the expression is evaluated, and if the condition is false, nothing happens. The typical use of the if statement is within a for loop. We will start with a simple example. We will say that I is going to iterate over 1 to 5, and in the body of the loop we're going to say print I. But we are going to put a condition. We will print I only if I is greater than 2. You can see that when we press enter we get only 3, 4 and 5. For I equals 1 or 2 the condition was false and nothing happened. The if statement is a nice way to have control over the statements inside a for loop. Finally, we'll give an example of how to combine for loops with if statements to solve problems in statistics. We will take the typical situation where a parameter is itself a random variable. For instance, Sz is taken from a Poisson distribution with lambda equals 44. So I don't know the value of Sz, but I know that it's probably around 44. Then I draw a random number from a binomial distribution with parameter size equal to Sz, the unknown parameter, and prob equals 0.3. The result is 15. Given this number 15, what is the probability distribution of Sc? One attractive strategy to answer this kind of question is to repeat the particular scenario to replay it as many times as we want. And we can see what are the typical values of Sc that tend to produce 15 in the second call. As we will resample this scenario a large number of times, we need to create a vector where we're going to store the value of Sc. I'm calling it values. And I put in it the special value NA, which represents not a number, that's nothing at all, 1,000,000 times. Then I create the for loop, where I will run from 1 to 1,000,000. And in the body of the for loop, I'm going to rerun the scenario above. First, I sample a new value of the variable Sc, and because this is one statement, I put a semicolon after that to say that this is finished. Then I sample a binomial random variable where size is equal to the new value of Sc. And again, this is an entire statement, so I put a semicolon. If the result is not 15, I don't care. But if it is 15, then I'm interested in it. So to test the condition, I'm defining x as the result of the previous operation, and I'm putting this inside an if statement. So when the result is 15, I just keep the value of Sc that has produced 15. And I store it in the vector values at position I. It takes a few moments to run the whole for loop. If I look at the first values that I obtained, I can see that most of them are still NA. It means that in these cases the condition was false. Nothing happened during this iteration of the for loop. Let's see how many times we did not obtain 15 in the simulation above. For this we use the function is.na, which returns true if the value is NA. We can see that this is the overwhelming majority because it happened over 908,000 times. So we obtain 15 approximately 10% of the time. We're going to keep only the interesting values. It is the values of Sd when the second call gave 15. I define the vector v, which contains the values of the vector values, which are not NA. And I get approximately 91,000 numbers. We can now inspect which values of Sc gave 15 in the second call. The simplest way to do this is to use the function table, which counts how many times a particular value is present in a vector. You can see, for instance, that the value 27 was obtained 7 times, the value 28 was obtained 11 times, and so on. We can represent these results in a graphical format with a plot function. We get a nice looking plot that shows how many times a particular value of Sc was obtained when we obtained 15 in the second call. The value that we obtain the most often is 44. This is the value that was most frequently picked in the first call, when in the second call we obtained 15. Those are not probabilities because you can see that the numbers are way above 1, but I know that I've got approximately 91,000 numbers, so I can easily turn them into probabilities. I just have to divide the result of table by 91,210. And this now gives me the complete probability distribution of SZ, given that we have obtained 15 in the second call. In summary, the for loop in combination with the if statement is really useful to solve this kind of Bayesian problems. That's all I wanted to share with you. Good luck at the quiz, and see you at the tutorial.